This is a nice. Here's a photo of the ring arriving at Fermilab, which is where the experiment's located. So just by way of introduction, we all know that we have the standard model of particle physics, which does a very good job of describing most of the data that we have available to us. But we also know that something's missing because it doesn't include things like dark matter or gravity, and doesn't explain the cause of the matter-antimatter asymmetry in the universe. So we're trying to find this new physics that could incorporate all of this into explaining how the universe works. And the way I see it is that there's kind of two main routes that we use to do this. There's the high energy frontier, which is things like the LHC, which uses Einstein's E equals mc squared. So if you go to higher energies, then you reach higher masses of particles that we might not know about. And then the alternative route is the high intensity frontier, which is what the g-2 experiment uses. And this is kind of more based on Heisenberg's uncertainty principle, where if you measure something really precisely, then you get to glimpse at the higher energy particles, which can only exist for really short amounts of time. So the more energy they need to borrow, the less time that they can pop in and out of space for. And the higher precision that you can measure something to means that you can see these particles that way as well. So what we're trying to measure to high precision is the magnetic moment of a muon. So all particles have an intrinsic magnetic moment, which basically determines how the particle interacts with the magnetic field. And the strength of this interaction is determined by this factor G, which is known as the gyromagnetic ratio. So this is essentially what we're trying to measure. And what this means is that when a particle is placed in a magnetic field, its spin precesses around the magnetic field, and the frequency of that precession is determined by this G factor. And so by measuring the spin precession, we can see the strength of the interaction of the muon with a magnetic field. And we want to measure this to really high precision so that we can compare it to the theoretical result, which we can also calculate to incredibly high precision. And then we can see if there's any discrepancies there. So this plot on the left shows some of the most precisely measured quantities in particle physics. And you can see that the muon g-2 is one of the most precisely measured that we have, and in fact I think is the most precisely measured quantity at a particle accelerator. So if we went with Dirac's original prediction, then G would be exactly equal to 2. But because we know that we can have loop corrections, so we can have other particles interacting, so rather than having the basic interaction of a muon with a magnetic field or a photon, we can have other particles contributing through loops. And this changes the value of G to make it slightly greater than 2. And what we're actually trying to measure is the difference from 2. This is sensitive. You can have any particles in existence in these loops. So therefore, we're sensitive to any potential particles that we don't know about. And muons are particularly interesting because they're heavier than the electron, which this mass advantage means that you have greater sensitivity to higher masses than the electron, because it goes by the mass squared. So the tau would potentially be more sensitive to higher energies, but is much more difficult to measure because conveniently the muon decays nice and neatly to an electron. So this is a basic summary of the components of the theoretical prediction. So we start with Dirac's prediction with the basic diagram where it's exactly equal to 2. And then we add on all the various different loop corrections, which are divided into different sections. So the biggest contribution is from QED, and the first correction was done by Schwinger, and this is the first order QED correction, but it's actually now being calculated up to 10th order in QED, including more than 12,000 diagrams, and cross-checked, I think, and that's the second most, the second biggest contribution to the value. But then we have the more complicated contributions. So the electroweak slightly easier to calculate, and the hadronic contributions are the most difficult to calculate, because there you're in the non-perturbative regime. And so despite this being quite a small contribution to the theoretical prediction, it's actually where most of the error comes from. So it's the dominant uncertainty in the calculation. And so this is the part that most of the work is being put in at the moment, to try and improve upon the theoretical result. And then obviously beyond this, any extra physics could contribute that we don't yet know about. And so this is where the new physics could come in. So this is the status before the last result. So up here we have the experimental measurement that was done at Brookhaven about 20 years ago. And in red is the result, the first result that was published at the Fermilab experiment in 2021, based on the data that was taken just in the first year of running the experiment. So this has about the same uncertainty as Brookhaven result, and the two agree very well. And they're both very statistically dominated, so we can combine them and get this experimental average. And then the best theoretical prediction that we had was released in what we call the white paper, that was published in 2020, and that combined all the theoretical predictions that we had from all theorists that were working on this in the G-2 Theory Institute. And you can see that the prediction from that disagreed with our experimental result at a level of 4.2 sigma. So this was intriguing and also backed up the discrepancy that Brookhaven had measured 20 years ago. So we want to see if this is the sign of the new physics that we're looking for, and so analyze the rest of the data that we have to see if the result still agrees. So I'm going to focus on the results from the second and third years of running. So this isn't all the data that we've collected, but it has about 4 times as many statistics as the run 1 result. So we should improve the result by about a factor of 2. So just to go back to the theoretical prediction, as I said, it has all these different components, and the dominant uncertainty comes from these 2 hadronic contributions at the bottom, which are divided into 2 sections. The hadronic vacuum polarization, which has diagrams like are shown here, and then the hadronic light by light. And out of those 2 contributions, the hadronic vacuum polarization has the largest uncertainty, and is more than 80% of the total uncertainty on the theoretical prediction. So you can see in the plot on the right here that QED is basically the entire contribution to the theoretical prediction, but the error is highly dominated by the hadronic contributions. And it's actually the hadronic vacuum polarization which has caused some discrepancies between various different theories at the current time. So I'm not a theorist, so I can't give you every detail about this, but I'll try and summarize it quickly. So for the hadronic vacuum polarization, you have diagrams like the one shown here. So across the muon, you have this hadronic bubble. And the way that this was done for the white paper was using a data-driven method or dispersive method. So you take this loop here, and then if you cut it in half, you can use E plus E minus goes to hadrons data. So it's data-driven, and you can use that to calculate your theoretical prediction. So they take the data for this E plus E minus goes to hadrons from various different experiments, which you can see in the plot. And there's always been some discrepancy between the various different measurements, and the variation between the measurements was taken into account in the prediction that they calculated for the white paper. But very recently, new results from CMD3 were released, and this is the point right at the bottom. And you can see that this disagrees with basically all the other measurements that have been made by a fair amount, and indeed with the CMD2 result. And so investigation is ongoing as to the cause of this, and how to include this in the theoretical prediction. So they're working hard on that, but we don't have any conclusion at the moment. In addition, there is also lattice QCD, which is becoming much more precise now. So at the time that the white paper was published, the lattice QCD results were much higher uncertainty than the dispersive approach. But just before we released the first result, the BMW collaboration published a lattice QCD prediction at much higher precision. So in the plot, you can see various different lattice QCD predictions from different groups. And then you can see that the BMW result is at much higher precision than the rest of them. And again, the grey band shows the value that you get from the dispersive approach, and you can see that the BMW lattice result disagrees with the value that was published in the white paper. And it's between that white paper theoretical prediction and the run one experimental result. So it's kind of in the middle. So the other lattice groups are cross-checking the BMW result at the moment. So far, they've only checked in certain regions, and the intermediate stages agree. But the hardest part of the lattice calculation is in the edges. And so they're working hard at the moment to see if they agree with the BMW result or look for any discrepancies. And they hope to try and resolve these various discrepancies in the same time frame as us publishing the result from the entirety of our data set. But at the moment, the theory is a little unclear. So moving on to what I know much more about, which is the experiment. So here in the photo is the g-2 ring, and the muons come in at the top here, and then this is a big magnet that was moved from Brookhaven to Fermilab. So the principle of the measurement is that you inject muons into the storage ring, and then they go around in the magnetic field. So both the momentum and the spin process. But because G is slightly greater than 2, it means that the spin process is slightly faster than the momentum. And by measuring the difference between these two frequencies, we can determine the strength of the G factor, gyromagnetic ratio, or actually a mu is what we measure, the anomalous magnetic moment, which is the difference from 2 essentially. And you can see that this is determined by omega A, which is this spin precession frequency. So if we measure that and the magnetic field to very high precision, then we can extract this anomalous magnetic moment. So to put into context the uncertainty that we're aiming for, which is 140 parts per million. Here is the g-2 jigsaw. So if you lost one piece of this jigsaw, that would be the equivalent of 1,000 parts per million. If you took 100 jigsaws and only lost one piece in all 100 jigsaws, that's the equivalent of 10 parts per million. So this is about the same precision as what was measured in the SAN3 experiment, which measured g-2 for the muon, which was done in 1976. So the precision that we're aiming for is if you only lost one piece of a jigsaw in 7,143 jigsaws. So that's the precision we're aiming for, which means that every detail in the experiment counts. We have to understand every part of what we're doing. And so in order to do this, the experiment obviously has more statistics, but we also improve the detectors and have better understanding and control of the beam from the Fermilab accelerator complex. So this is the Fermilab accelerator complex, and what's happened is that we get protons from the accelerator, and then this triangle here was the old antiproton complex, which has been redesigned as our delivery ring. So the protons get smashed into a target to produce pions, and the pions decay as they go around the delivery ring, so that by the time they reach the g-2 building, we can inject a pure beam of polarized muons. And the reason that we moved to Fermilab was because the accelerator can provide us with more muons at a lower instantaneous rate, which improves the ability to make the measurement. So this is a summary of how the muons are produced. So as I said, you take the protons that are smashed into the target, and then we select pions from this using a lithium lens at slightly higher energy than we want the muons to be. And then as they go around the delivery ring, these pions decay into muons. Well, positive muons is actually what we use. And so we go around the delivery ring about 4 times, by which point most of the pions have decayed to muons, and we have a pure beam of muons. We also, as it goes around the delivery ring several times, you get separation between the different types of particles. So in pink is muons and in green is protons. So by the time they've gone around 4 times, there's a good separation between them. So we could just inject the muons into the beam. And conveniently, through the pion decay, we get a naturally polarized beam of muons. So by spin conservation, it means that when the muons are produced, the spin must be pointing in the same direction. And so that's convenient for the measurement. So this is just a quick summary of how the experiment works. So the muons come in through these magnets at the top, the red ones, and they enter the ring through what we call the inflector magnet. So the inflector magnet essentially cancels out the magnetic field in the ring so that the muons can enter on a straight path. And just before the inflector magnet, we have what we call the T0 and the IBMS, which are detectors that measure the temporal and spatial distribution of the beam at the point of injection. So once they've gone through the injector magnet, we can't put the inflector magnet in the beam, because otherwise when the muons come around again, they would hit it. So it's actually slightly offset from the ideal orbit. So then we have these kickers. So there's 3 kicker magnets which are located here, and these give the muons a slight kick to put them on to the right path in the center of the magnet. So the kickers are designed to have a pulse that lasts over the muons that are injected, but has turned off by the time they come around again about 150 nanoseconds later. So then in addition, we have quadrupole magnets, electrostatic quadrupoles, to focus the beam. Otherwise, it would diverge vertically and we wouldn't be able to store the muons as long. So there's kind of 4 sets of quadrupoles around the ring, and it covers nearly half the total circumference. So this basically like squeezes the beam down so that we can store the muons for longer. And then we have our detectors. So the main detector is the calorimeters. So we have 24 calorimeters that are located around the inside of the ring, so that we can detect the positrons from the muon decay and measure their energies. And you can see the calorimeters here. So they're made of lead fluoride crystals in an array that's 6x9. And then in addition, we have the tracking detectors. So these are only in 2 locations around the ring, because that's the only space that we had left. And so these are straw trackers, and this means that we can track the path of the positron, so we can see exactly where it came from. And here you can see if you're a muon inside the storage region, this is what you'd see of the trackers. And they have there are 32 stores across each tracker, and then we have 8 modules in a tracker station. So as I said, we basically want to measure the spin precession and the magnetic field. But what we actually measure is 2 frequencies, because that's how you get the most accurate results. So this is the final equations. So we have the spin precession frequency, and then the magnetic field is measured using NMR techniques. So that's another frequency measurement. And then these other quantities are known to incredibly high precision, so that doesn't really affect the measurement. And then the additional complication is that once we have the measurement of the magnetic field from NMR, or the precession of a proton, we also want to convolute that with the muon distribution, so that we know what field the muons experienced at the point of decay. So I'm going to talk through how we measure each of those components. So starting with the magnetic field, so this is a kind of diagram of the magnet, and as I said, we want to measure the magnetic field very precisely, but that also involves us wanting to have a very uniform magnetic field. So the magnet was designed with all these various different things that you can adjust in order to improve the uniformity of the magnetic field. And then this is a video showing the magnet shimming. So that's how the kind of red points evolve over time. And this is them tuning the various different knobs on the magnet. And then at the end, they stick really tiny pieces of metal onto the magnet to make it as uniform as possible. So these pieces of metal were less than the width of a human hair in places, and this is the effect that putting those on have. So now you can see the final field uniformity in red, and that's compared to the field uniformity they achieved at Brookhaven in blue. So we achieved much better uniformity than they had. But even though we've made the field as uniform as possible, we obviously want to monitor the field over time, and we have different ways of doing this. So the field that we want to know is the field that the muons experience, but obviously we can't measure that while the muons are in there. But we do have this trolley that we drive around approximately every 3 days when we're not putting muons into the ring, to measure the field exactly in the storage region. So the trolley has these 17 NMR probes, and then it drives around the ring, and you produce these 2D field maps at about 8,000 points as you go around. And then you can combine these to make the variation in the magnetic field. So you can see that across the storage region, the variation is less than 1 part per million. So it's a very precisely calibrated magnetic field. Obviously, while the muons are in there, we can't use the trolley to measure it. So we do want to track the field over that. And for that, we have these fixed probes that are at the top and bottom of the storage region. You can see kind of roughly where they're located in blue for the top ones and then orange for the bottom ones. Or here's like where the trolley would be and then the probes at the top and bottom. And so these monitor the field continuously. And then by comparing that with the trolley data, you can get the measurement in between the trolley runs. So here you can see the trolley runs are the red points, and then you have the field that you interpolated between those 2 points using the fixed probes. So then you know the field across all time. The field is also calibrated. This is done in between each of our years of data taking over the summer when the accelerator is turned off. So we have various different ways to calibrate it. So first of all, we have this, what we call a plunging probe, and that's used to calibrate the trolley probe. So you kind of put the plunging probe in and then move the trolley probe to the same location, and then you repeat this, and then you can calibrate each of the probes on the trolley. And then we additionally calibrate the plunging probe against this water probe and a helium-3 probe as well, to get the best understanding of exactly what we're measuring in the NMR probes around the ring. So that's how we measure the magnetic field. Next, we have the anomalous precession frequency, so how the spin rotates. Next we want to measure the muon distribution, which we convolute with the magnetic field. So this is done using the tracking detectors. So when a muon decays to a positron, it will sometimes pass through the tracker, and then it will produce a series of hits, which means we can reconstruct the track, and then we can extrapolate this track back to find the point at which the positron decayed. So from this, we can reconstruct the muon beam distribution. So you can see this in the plot on the left. So this is muon beam distribution across the whole time in the fill. And then on the right, it has the magnetic field overlaid. And so by convoluting those two, you get a measurement of the field the muon has experienced. We actually measure the beam distribution as a function of time. So you can see how much the beam moves over time. So this is the beam distribution, and then the time's counting up. And then you can see the variation in the radial position and the radial width in the plot here, and then a summary plot there. And these become important because of the detector acceptance. So depending on where the beam is in the ring, it changes the acceptance of our detectors, and this has to be included in the measurement, which comes into play in the measurement of the precession frequency. So to measure the precession frequency, we basically use the fact that the positrons preferentially decay, well, the highest energy positrons preferentially decay in the direction of the muon spin, again, through the convenience of how the standard model works. Essentially, this means that as time goes on, the muon acts a bit like a lighthouse, spraying out positrons around, and so you get, when the spin is pointing in the direction of the momentum, you get more high energy positrons, and when it's pointing away, you get less. And the plot on the right kind of shows this. And this means that in essence, if you put an energy cut and then you just count the number of positrons that you see as a function of time, then you'll see the oscillation in the number, which gives you the precession frequency that we want to extract. And if you do that, then you end up with what we call the wiggle plot. So you can see the precession frequency in the wiggle here, and this is kind of counting up as we take data. So far in this plot is only half an hour of data taking, and you can see how clear the oscillation is already. And then you could just fit this distribution with a simple exponential decay that comes from muon decay, and then this oscillation frequency. Well, you could do that, but it's actually a bit more complicated, because if you just were to fit with that simple function, if you take a Fourier transform of the difference between the data points and your fit, then you end up with this plot on the right, and you can see that you don't get a flat distribution. In fact, several frequencies stick out, and these correspond to the beam motions. So from the tracking detectors, you can see the beam swimming around, mostly radially, but it also changes vertically. And so these are the contributions that you see in this Fourier transform. So actually what we do is fit with a much more complicated fit to take into account these beam motions. So rather than doing a 5-parameter fit, we do a fit with about 24 parameters. And you can see that if you do that, you end up with this red line. So these frequencies have disappeared, and you also get a much better chi-squared value. So that is the basics of how we make the measurement with these 3 components. Then on top of that, we have some additional complications. So these are applied as corrections. So we have corrections from what we call the E field and the pitch. Then we have 3 corrections that essentially come from the phase of the muons changing over the fill for various reasons. And then there's corrections to the measured value of the magnetic field that mostly come from our pole systems, which is the kickers and the quads. So I'm going to try and talk very briefly through these, but I don't really have time to go into much detail. So to start with the first 2, which we call the E field and pitch correction, I showed the basic equation, but because we have the electrostatic quadrupoles for focusing the beam, an electric field looks like a magnetic field to a moving particle. And so you get these 2 extra terms. So the first one is the source of the E field correction. So this term is mostly cancelled out because we choose the value of the momentum to be at the so-called magic momentum, which means that the value of gamma is such that this term should be 0. But obviously in the real world, we don't have all the muons exactly at the right momentum. And so there's a small amount that we have to apply to correct for this term here. And the way we measure that is when the muons are injected, the higher end, you get higher energy, higher momentum positrons and lower momentum positrons fall at different positions across the storage region, and then they also catch up with each other. And so by looking at the distribution as a function of time at very early times, you can extract the radial beam distribution. And this basically tells you the spread in momentum of the muons, and so you can calculate this correction. The other correction is because we can't inject the muons all to be exactly perpendicular to our magnetic field. So some of them are moving up and down, which is why we need the quadrupoles in the first place, so that they don't all fly out the ring. And by measuring the beam distribution vertically, it allows you to calculate the correction that we need for this, which is known as the pitch correction. Then there were the 3 other corrections to the spin precession, which are all to do with the phase. So the basic fit is this, and so in this oscillation, you have the spin precession frequency, but you also have this phase, which is the phase of the muon at injection. But if this phase were to change over time, then that would leak into the measurement of the spin precession frequency. So we need to account for any variations in the phase that change as a function of time. So the first one we call the phase acceptance. So the position that the muon decays has different phases across the different decay positions in the ring. But we also know that the beam position changes as a function of time. And so that means that you're selecting different phases from this distribution. And so the phase changes as a function of time. This was particularly bad in run 1, but has been improved for run 2 and run 3, and I'll mention that in a minute. Then we have muon losses, and this can change the phase because the momentum is the phase is correlated with the momentum of the muons, and we lose more low energy momentums at early times than high energy momentum, high momentum muons. And so this means that the kind of average phase changes as a function of time. And then lastly, there's this correction called the differential decay. And this is because if the muons have different momentum, then they have different gamma factors. So actually, the muon lifetime is different. So they're depending on the momentum, they decay at different times. And because the phase is correlated with the momentum, this means the phase changes over time. So we divide, these are all basically phase changes, but they're divided into 3 different corrections that we apply. Then we have the corrections to the magnetic field. So these are due to the pulse systems, which is the kicker and the quadrupoles. So for the kicker, although the main kick is just on the first time that the muons go around the ring, there is some residual kick that's left over throughout the fill, and this obviously impacts the field that the muons experience. This was measured directly using a magnetometer, and this is the result that was from run 1. And then you have the electrostatic quadrupoles, and so you can see how these change the field as a function of time due to kind of vibrations. And so here the gray bands are when the muons are injected into the ring, and then you have the variation over time. And there's a zoom in on the bottom, and these variations were measured with a probe that was designed to go in the vacuum, and then you pulse the quads and see what you detect with that. And this was improved for run 2 and 3 as well. So this is a summary of the uncertainties that we had for run 1. So as I said, it was very statistically dominated, and obviously we have more data in run 2 and 3. But then if you look at the systematics in more detail, you can see that the quad transient I just talked about is the biggest of the systematics. So we really focused on that. And then second biggest is from the phase acceptance, which is the variation of the phase based on the average position of the beam. So here, I'm now going to just quickly summarize the improvements since the run 1 measurement. So divided them into kind of 4 rough categories. So obviously statistics, we have a lot more data, and you can see here the run 1 result was just based on the part in red, and now we have the data in blue and green. And then in black, it's showing the statistical precision that you obtain based on that amount of data. The table summarizes the statistical error. So in run 1, it was about 430 parts per billion. And then in run 2, this is reduced by more than half to about 200 parts per billion. And then if you combine them, you get 185. So then there were improvements in the running conditions. So first of all, in run 1, we had this complication due to some of the resistors for our quadrupoles. So 2 of the quad plates had damaged resistors, and this meant that there was actually quite a big difference in the beam storage as a function of time. So you can see here, this is the vertical position of the beam as a function of time. And in run 1, it changes quite dramatically over the course of the fill. But this is dramatically reduced in run 3 and run 2. And then in this plot, this shows the phase acceptance. So you can see that this is hugely reduced just due to the fact that the beam isn't moving as much. So the overall impact of this was to reduce the phase acceptance uncertainty from 75 parts per billion in run 1 to 13 parts per billion in run 2. And then this also helps with the spin precession measurement itself, just because the beam oscillation frequencies are more stable. So, because when the quadrupole strength was changing over time, it meant that the frequency of the beam oscillations was also changing, which made it a lot more difficult to fit. Then we also had problems with the stability of the temperature in the hull. So you can see in run 1, the temperature in the hull changed a lot, but this resulted in the temperature of the magnet changing considerably, which leads into the measurement of the magnetic field being much more complicated. In run 2, we added insulation around the ring. So you can see in the photos at the bottom that it was blue, and then we put the insulation in white. And this had some impact. The variation in temperature was reduced, but it wasn't until run 3 that we actually managed to stick at a stable temperature. And that was because we introduced a much more stable cooling system in the hull, which kept the hull temperature constant and therefore the magnetic temperature constant. And so this means that the magnetic field was also more stable, and therefore improved the measurement. There was also a lot of work done on the kickers. So in run 1, the kickers weren't kicking quite as hard as we'd like, which meant that the beam wasn't going quite centered in our storage ring. And this is shown in the plot on the left. This was actually only done for the last part of run 3. So only the last 18% of the data in the run 2-3 analysis. But you can see that before these changes were made, you get the black distribution. And then after, you get the red distribution, which is much closer to 0. And then you can also see that the mean radial position, so the amount the beam is swimming as it goes around the ring, is much reduced, which also improves the measurement of the spin precession frequency. So then there's improvements to the systematic uncertainties. So the quad transients, as I said, this was the largest systematic that we had in run 1. And for the run 1 measurement, we'd actually only measured the change in the magnetic field using this dedicated NMR probe that goes in the vacuum in 2 locations. And so you can see those 2 locations indicated on the plot here. But for run 2 and 3, they developed this thing that meant that the probe could be easily moved around the ring using the trolley rails, and we could measure it across the entirety of the 4 quadrupoles, and so we knew exactly what it was at all the various points. And this dramatically reduced the uncertainty. So we went from 92 parts per billion to 20 parts per billion. The kicker transients were also improved. So this was done using this Faraday magnetometer. There's a kind of picture of it here. And basically by improving the vibrational noise on the equipment, it improved the measurement. So in black, you can see the run 1 measurement, and then in red, you can see the run 2, 3 measurement. And so you can see that the kind of variation or from the vibrations is much reduced. And then so this decreased the uncertainty from 37 to 13 parts per billion. And then lastly, just to run through quickly some analysis improvements. So one of these was the pile up. So if you have 2 low energy positrons that arrive at the same time in the calorimeter, you might reconstruct this as just 1 high energy positron, which could then enter into your spin precession measurement incorrectly. But we improved the way that the clustering was done. So we could better differentiate between 2 positrons that might arrive at the same time. And then there were also changes to the pileup, the way that the pileup correction was calculated, which also improved the measurement in general. And then there's also the E-field correction, which is kind of to do with the differential decay that I mentioned. And this is a new thing for run 2 and 3, which we didn't include in run 1. So it's basically the correlations between the momentum and the time of injection. And because the E-field correction is measured using the early beam distribution, this is important in the calculation of the E-field correction that we have to apply. So here is just a summary of the uncertainties. So the red bars are the uncertainties we had in run 1, and the blue is the uncertainties in the measurement for run 2 and 3. And you can see that in all cases, the errors were reduced. And actually, the goal that we had for systematic uncertainty was 100 parts per billion, and we have achieved a systematic uncertainty of 70 parts per billion. So that's actually better than what we aim to do, which is good news. And then you can see a summary of the contributions from the different uncertainties. And now the quad transient isn't the dominant uncertainty. And then there's a summary of the statistical and systematic errors in the table at the bottom. So actually, although both measurements are statistically dominated, and the systematic error has reduced proportionately, so the ratio between the 2 has stayed roughly the same. So when we're doing the analysis, it's blinded, and the way that we blind it, because we're measuring frequency, we can just change the frequency of our clock by a small amount. And this is done by 2 people outside the collaboration. So they choose the value and they write it in 2 envelopes and keep them hidden from us until we decide that we're definitely ready to unblind. And then we open the envelopes. So this is at Liverpool, where we had our collaboration meeting. So it has to be a unanimous vote from the whole collaboration. As you can see, everyone agreed. And then this is James Mott, who was the analysis coordinator for run 2 and 3, opening the envelopes to see what the value actually is, so that we could put that in and see what the final result actually is. And here is the summary of the result. So I showed you the Brookhaven and run 1 results. And here the bottom point is the run 2, 3 results. And you can see that this has remarkable agreement with the run 1 result, with far reduced uncertainty. So the uncertainty is more than halved, down to 215 parts per billion. And again, this is a statistics dominated measurement. So because these are dominated by statistics, and then we can assume that the systematic errors are 100% correlated, we can combine these results from 1, 1 and 1, 2, and 3 to get the point on the bottom here. And then additionally, we can combine this with Brookhaven, and this is the final world average that we end up with, which is dominated by the 1, 2, 3 measurement. So then, and by coincidence, these measurements from Brookhaven and Fermilab on 1, 2, and 3 were done at very slightly different magnetic field values, which provides a good way to cross-check the result. So you can see the precession frequency as a function of the magnetic field strength, essentially. And luckily, we had 1, 1, and then Brookhaven, and then 1, 2, and 3 happened to lie in the middle. And these all lie on a nice flat line, which is good to see. So then to compare with theory, as I mentioned, the theory is a bit more complicated at the moment, and they're working hard to work out where these discrepancies come from, which is interesting in itself. So if we compare to the white paper, then the result actually has a more than 5 sigma discrepancy. But then we also have the complications from the new lattice calculation and the new CMD3 result. And so you can see in orange is just plotting the result that came from the BMW collaboration, which is much closer to the experimental value that we measured. And then this bottom point comes with a lot of caveats and is not a kind of proper theoretical result. This is by taking the CMD3 data only, ignoring all the other experimental results below 1 GeV, and doing the hadronic vacuum polarization calculation. This is kind of the result you would get. This is basically a kind of bounding case because you've ignored all the other experimental measurements. But we're expecting more data from multiple other experiments to come soon, and so we will hopefully that might determine something, and there's also a lot more work going on to try and understand this. So there's a caveat from Alex down here that he just did this as a kind of interesting exercise, and it shouldn't be taken as a serious theory prediction. So then just to summarize, this is the result that we just released, where you can see we got more than 2 times the precision that we measured in run 1 and compared to Brookhaven. And we've reduced our systematic uncertainties below the design goal that we had. But still there's more exciting times to come, because we've taken a lot more data since run 2 and 3. We've had runs 4, 5, and 6 is finished now as well. So we're in the process of analysing those, and hopefully we will produce a new result, and the theorists will resolve their discrepancies on roughly the same time scale for us to produce the final result with even better uncertainty. So thanks.
Thank you so much for a very nice talk. Those are very impressive results. I think we have a few minutes for questions. Please feel free to just unmute or raise your hand. Maybe I can get started. Is run 6 the last run, or are you planning to run for longer than that?
No, run 6 is the last one.
Okay.
We started taking it apart. Well, no, there's some magnetic field measurements going on, but the beam is going to mutui.
Okay. And do you expect from runs 4, 5, 6 that you will reduce the systematic uncertainty even more than you already did very impressively for runs 2 or 3, or do you expect it to be comparable?
Yeah, it should reduce a bit, but there's not so much further to go really anymore. But there have been some more studies, and there's more magnetic field measurements going on at the moment, which will be applied. And obviously the kicker strength was only improved right at the end of run 3, and that has stayed for the whole of run 4, 5, and 6. There was also improvements to the quadrupoles where they put in this RF, which further reduced the beam oscillations, so that should also help. So hopefully a little bit better, but improving on 70 parts per billion is quite difficult.
Fair enough. Does anyone else have any questions? If not, then I have one last one. I'm curious whether there's also a forthcoming paper on the electric dipole moment, as you can also, I think, measure that with this experiment.
Yeah, actually, hopefully very soon. So, well, the result from run 1 should come out soon. It's in review process at the moment.
Okay.
We wanted to wait until this result is died down before getting the collaboration to go through a whole nother review process. But hopefully, like by the end of the year.
Nice.
You don't happen to have snuck in any backup slides about that measurement, do you?
I don't know. I don't think I did. Oh no, I did. Here you go. So basically, if a particle is to have an electric dipole moment, it adds a term to the precession frequency that you measure, but this electric dipole moment is, well, dominated by a term that, instead of being in the direction of the magnetic field, is perpendicular to the magnetic field. So the effect it has is tilting your precession plane. And also it would change your precession frequency by a small amount, but way below what we could actually measure. So the way that you measure it is by looking for a tilt in the precession plane that's out of phase with the spin precession frequency. So you just look for up and down, and actually in the Fermilab experiment, because of the tracking detectors that they didn't have at Brookhaven, we should get an awful lot more tracks than they had, which means that we should be able to improve upon the electric dipole moment measurement by about 2 orders of magnitude.
Can you explain or just briefly walk me through this plot on the right? It should be straightforward, but I'm not.
Yeah, well, it's probably not as straightforward. So the yellow is if we had 10 million tracks, which is basically what the Brookhaven measurement had. So they measured the EDM to just above 10 to the minus 19. And the main problem with measuring the EDM is that if you had any radial field component, that would also tilt your precession plane. And so it's actually kind of how well you know your radial field that determines how well you can measure it. So that's with knowing the radial field to 40 parts per million. And then if they had 10 billion tracks, then they'd measure it to just above 10 to the minus 20. And then the last two is the rough guesses for what we might be able to do at the Fermilab experiment. So if we can measure the radial field to 10 parts per million, you get what's in red. And if you can measure it to 1 part per million, you get what's in green. And there's been a lot of kind of clever studies done to try and reduce the radial field uncertainty. and measure it more precisely as we've taken more data.
Okay, thank you.
All right. I think.
So maybe one question. So if we take, let's say, these new lattice results too seriously, like BMW, so roughly speaking, loosely speaking, let's say, how many sigmas will be like this tension?
I think, well, I can't remember exactly, but I think it's about 2 sigma between the lattice and the experiment. I think it's about 2 sigma both ways, 2 sigma tension with the theoretical result and 2 sigma tension with the experimental result as well.
And this says this new E plus and minus that is even smaller, right?
Yeah, that's actually closer to the experimental result, and disagrees with their own experiments' last results. So there's a lot of work going on to understand what's going on there, and obviously compared to new results from like Bell and Bess and other experiments as well, which should be releasing data soon. I know that there's a lot of work going into this at the moment, but I don't know all the details because I'm not a theorist, I'm afraid.
Okay, thank you.
All right. I think we can close here. Thank you so much for this interesting presentation and for getting up early. And hopefully see you